Yeah, thanks again for inviting me to give this guest lecture. And I'm really glad to have this opportunity to share with all of you about an exciting and emerging research area, which is geotechnical seismic isolation. And I believe Juan has already introduced to you the background of this topic. So this is part of the larger area of geotechnical earthquake engineering. And I think this is the name of the subject that you are studying now. And whenever we talk about earthquake engineering, there are a lot of complex concepts, and probably there are also a lot of mathematics. And that is because when we talk about earthquake engineering, there are a few important elements. One is dynamic, the second one is nonlinearity, and the third is probabilistic. If Horn has covered all these three elements in his course, then that means your subject should be quite a challenging one. And of course, geotechnical seismic isolation is actually part of this geotechnical earthquake engineering family. And there's no doubt that this is also quite an advanced and challenging topic. But I promise you today that there will not be any equations. And so I hope you will enjoy this presentation. So let's start with this slide. That is a very recent earthquake that occurred in Turkey just early last month. And there were actually two major earthquakes on the first day of this series of earthquakes. The first one was magnitude 7.8, and the second one was magnitude 7.7. And the sad thing is that it took away more than 50,000 people's lives and injured more than 120,000 people, and millions of people were affected, and also more than 1 million people were left homeless. And of course, there's no doubt that the earthquake has damaged a lot of buildings, and so the damage loss is actually significant. But if we try to ask ourselves whether this event or this consequence is actually unexpected, at least to me, it was not. So it's for an earthquake with that magnitude, with magnitude 7.8, 7.7, which were actually the largest ever in the history of Turkey, and it actually struck a relatively rural area of Turkey. And also, as we all know, the buildings there were not built to a very high standard. So it is actually not too surprising to see such a high level of damage and large number of deaths and injuries. But the problem is, what is even worse is we actually see similar situation all around the world. There have been rapidly growing web population all around the world, and many of these regions, cities, are actually located in high seismicity region. For example, within Turkey, we have Istanbul, which is another city of very high population in Turkey, and that was actually struck by a also quite a large magnitude earthquake, 7.4 to 7.6, back in 1999, just 23 years ago. And it also took away more than 10,000 people's lives at that time. So these things seem to be repeating. And if we look at other parts of the world, for example, a neighboring country in Iran, we have Tehran, which is also in a high seismicity area, also with high population. And in America, we have Mexico City, we have Lima in Peru, we have San Diego in Chile, and we have even more cities of high population in Asia, including Mumbai in India, Dhaka in Bangladesh, Manila in the Philippines, and Jakarta in Indonesia. All of these are located on high seismicity regions. So we can imagine that if a similar earthquake with magnitude around 8 that struck one of these cities, I think the consequence would be unbearable. And in these few years, there are a lot of people who are talking about sustainable development, sustainability. But people mainly focus on decarbonization, net zero, or even carbon negative. These are the main topics that people are talking about. And there are actually very few discussion about earthquake disaster or natural disaster in general. And in fact, as we all can imagine easily, earthquake disaster is actually highly related to the sustainable development of a region, of a city, of a country, and also of the whole world. Because when a disaster occurs, it will actually affect the economy of the affected region. And because of the globalized nature of the whole world, the economy and also all the population in the world would also be affected. And it has actually been recognized by the United Nations, and there is actually an office for disaster risk reduction, which has a role to actually specifically address this matter. And so we actually know that sustainable development and disaster risk reduction are mutually supportive objectives. And as civil engineers, we are now asked to design green buildings, right? And actually, people are also talking about the importance of considering disaster resilience as part of a design of a green buildings and part of the design for sustainability. For example, there are some kind of quite famous engineers. They are mainly located in the US. And they also said that it doesn't make sense to call green buildings sustainable if they can't withstand extreme seismic shaking or hurricane. And even a major person in the US Green Building Council also said that disaster resilience is another dimension to think about while we are pursuing green building. So I hope that by this introduction, you would have a better understanding why we actually need to consider earthquake resilience, even when the whole world is just talking about sustainability nowadays. And come back to the topic, and which is also, of course, related to what I have just mentioned. In fact, such kind of earthquake disaster is something that we can, as engineer, we can do something to prevent it, because we know that earthquake-resistant technologies do exist. For example, I'm showing you a number of advanced development in the area of earthquake-resistant technologies. We have advanced dampers, which was actually used for vehicles, but nowadays it can also be used for building design. For example, this meteorological fluid damper, I actually started researching on this more than 20 years ago. And this is a fantastic technology. There's no doubt about that. And of course, we are also using control theory, including AI, like proxy logic. These can also be used for calculating the optimum force for controlling vibrations in the building. Okay, but the problem is they are typically expensive technologies. These kind of dampers or seismic isolation techniques are all expensive. They might actually take like 20% of the whole construction cost. And so it would make the whole construction cost probably too high. And the other problem is, as we know, these are advanced technology. It involves new technologies, AI. These are something that typical civil engineers do not understand, right? So this kind of expert knowledge for the design or even for the installation part is actually missing in the civil engineering industry. And that's why these kind of advanced earthquake-resistant technologies actually cannot be used very commonly. Okay, so there is actually an equation, but I promised that there shouldn't be an equation, right? Let me remove it, okay? And the other technical aspect why these advanced technologies cannot may not be the most suitable solution is that, so imagine if we install these kind of dampers or isolation bearings onto the structure, actually, because they are part of the structure, right? For example, the dampers are actually within the frame of the building, like those on the left-hand side of this slide. And the bearings are actually between the lowest floor of the building and the foundation. Or we usually design a specific story for housing those isolation bearing. So that means they are part of the structure. And you can imagine that when the seismic wave is actually striking the building, part of the seismic energy can actually reach the structure before the energy is being dissipated, right? And the other thing that makes the design and construction a little bit inconvenient is that it involves modification to the structure and also addition of different devices, the dampers and the isolation bearings. So they are probably not the most ideal isolation strategy. So as engineers, we are always working with constraints, right? But if we want to solve a challenging problem, we have to think out of the box and think about what would be the ideal. So I let you think about it for 5 seconds.
You're asking the class, Kinho?
Yes, yes.
Okay. So you're gonna give them 1 minute to think about the ideal isolation
No,
system?
just 5 seconds, and it's
5
finished
seconds.
already.
Okay.
Okay.
Anyone has an idea of what is the ideal isolation system?
So of course, in my mind, and I think everyone can imagine that the most ideal isolation system would be a fully isolated one, right? So that means the foundation or the whole building is actually isolated from the ground. Okay, this is ideal.
So
Okay,
you mean that there is a gap, no? That there's air between
there is
the
a gap.
structure
There is
and
a gap.
the foundation. Okay. Yeah.
Yeah. Ideally, there should be just a gap without anything at all, right? But as I said there, as I wrote there, it is impractical, right? But I won't say that it is impossible because there must be technologies that can make it happen. For example, people are talking about magnetic levitation, right? So we can build Hyperloop that is actually based on this kind of isolation concept, right? But of course, if it is applied to a building, that would be considered very impractical, at least for now, right? But if we try to follow this direction of thinking, if we think that this is the ideal isolation system, why don't we fill it up with something that is trying to mimic the most ideal situation? So for example, as Juan just mentioned, can it be filled with air cushion? Can it be filled with water? So this can be something that people can explore, right? As researchers, we can explore, okay? And for now, we believe that, Juan and I believe that if we try to fill up this gap with soft materials, then it can probably try to mimic or try to achieve that ideal isolation. Okay, and so that's why we have been researching on this concept in the past 15 years or so. And so let me try to explain a little bit more about the isolation mechanism. And that is a little bit complicated, but I hope that you can also understand. So the first mechanism is actually based on the lower lateral stiffness at the isolation layer, and that is basically the soft material layer. And this is actually similar to the traditional base isolation system that is based on rubber bearing or a sliding bearing, okay? And so this should be relatively easier to understand. So if we try to put it into the context of soil dynamics or geotechnical earthquake engineering, we usually use the diagram here for simulating this dynamic soil structure interaction behavior. And so the soil properties can be represented by the spring Kx and K theta here, and also the dashboard, which are representing the damping. So that means when we have a soft layer, then Kx will be small. The stiffness on the ground will be small, and also the rotational stiffness would also be small. And so that would also facilitate the rocking isolation. And in fact, people have been also studying about the concept of rocking isolation. But until we started this study, people haven't really thought about changing the materials underneath the foundation. And so in our research, we try to replace the existing soil by softer materials. And so it can actually concentrate the deformation in the ground and at the same time reduce the deformation on the structure. And this is the concept of rocking isolation. And with the replacement of a softer material, then we can actually augment the rocking behavior and so further reduce the structural deformation. And thirdly, if we replace that foundation soil by a high damping material, then it can actually dissipate even more energy, and so less energy can be transmitted onto the structures. And so with the combination of these three mechanisms, we believe that concept can be very useful for protecting structures and the life inside the building. And if we put it in a very simple context, so the concept of this GSI system is actually like an airbag in a vehicle. As we all know, airbag actually prevents the occupant from striking interior objects. And the soft material layer that we are talking about using in the GSI system actually acts as a buffer and prevents the building from a direct hit of an earthquake. So I hope we all get some basic ideas about the fundamental or one of the major system of GSI. And based on what we researched at the beginning, so I've tried to define and also propose a new area of study, and I will of course talk about it in more detail in the rest of my presentation. And so what we define GSI is actually the category of seismic isolation techniques that are in direct contact with geomaterials, and of which the isolation mechanism primarily involves geotechnics. Okay, so that has already been published more than 12 years ago. And in that book chapter, I tried to put up this analogy because up to the year of 2009, people are very familiar with the concept on the upper half of this table, which are the so-called conventional structural seismic isolation techniques based on the use of rubber bearing, and some people call it a cushion. And other class would be about using sliding bearing. Okay, so those are quite commonly researched, commonly adopted since the 1980s. Okay, but then since we proposed the new concept based on geotechnics, we proposed a group of geotechnical seismic isolation. And by analogy, the one based on soft foundation layer would be analogous to the use of laminated rubber bearing. And the use of a sliding layer based on geosynthetic liner can be analogous to the use of spherical sliding bearing. And this is how the concept of geotechnical seismic isolation was born. And nowadays, after like 15 years of development of GSI, there are now 3 major branches of GSI system. So that means it has been expanded from 2 branches, as I just described in the previous slide, and to nowadays there are 3 branches, and they are categorized based on their isolation mechanisms. So let me introduce to you some of the recent research that have been done on each of these 3 branches of GSI system. So, for example, for the one that we are researching on, based on the use of recycled rubber mixing with soil, we have done a lot of different type of research. For example, on the right-hand upper corner, we have done centrifuge testing. So as you might know, there is a quite a well-known centrifuge laboratory in Cambridge, in the UK, right? And actually, there are also around more than 20 similar equipments all around the world, and we have also used the one in Taiwan to do similar centrifuge testing for the GSI system. And then we have a very well-known group in Europe, in Thessaloniki, in Greece, led by Professor Peterlakis. And so they have done numerical simulation to confirm the performance of the GSI system based on rubber soil mixtures. And they have also done full-scale field testing at a site close to their university. And apart from the use of rubber soil mixtures, there are also other schemes that can be used for facilitating soil foundation structure interaction. For example, what about if we do not fill up or do not replace the material below the foundation, but just remove the material surrounding the foundation? So this is what they call lateral disconnection, and this, in principle, is also similar to what we are researching on. And this is done by a group in Italy and also by Cambridge. And then instead of filling it up by using rubber soil mixtures, there's a researcher in Greece, in University of Petrus, and also in Bristol in the UK, who are researching the use of EPS foam to fill up the gap. And there is a consortium of researchers from Italy and also from China who are trying to fill up the gap by using rubber, and which is having a similar scheme as the one at the middle. And there is also another group of researchers from Chile and also from MIT in the US who are using an advanced analytical model to model the use of rubber soil mixtures for achieving GSI. And then because as we can see that the foundation material actually play a very important role, and it is important for us to understand the characteristics of these materials, especially under dynamic, under earthquake condition. So we have Juan here, your lecturer, who have done a lot of fantastic work on characterizing the material properties of the material using micromechanics. And then we have also a group of researchers also from Greece, the one that I just mentioned in the previous one, that is studying the shear modulus reduction and also the damping behavior under different shaking levels. And then we have a group from New Zealand who are also investigating the material properties based on the locally available materials. And then apart from rubber soil mixtures and also EPS geofoam that I have just mentioned, there are also other materials that can be used for achieving GSIs. For example, there is a group from Italy, from Napoli, Italy. They have proposed the use of super absorbent polymer for achieving GSI. And they have even established a spin-off company. That means they commercialized the technology and promoted it to the market. And we have a group from Turkey who are using EPS bead and EPS geofoam for achieving the same purpose. And we have a group from Japan, Osaka, Japan, who are using nylon fiber for filling up the gap surrounding the building foundation. And then let's move on to the second branch of GSI system, and that is based on sliding. And as I've briefly mentioned before, we have researchers who have proposed the use of geosynthetics, which in this slide we can see that which can be used for isolating the foundation. That means it is in direct contact with the foundation, or it can actually be put between soil layers so that it is what they call soil isolation. And so the concept is more or less similar, and both of them are based on sliding. And so that's why it belongs to the second branch of GSI systems. And in more recent time, there have been a lot of more different proposals that is based on also creating a sliding base to achieve GSI. And for example, a researcher, Giavo from ETH Zurich, has implemented the use of PVC underneath the foundation and then putting sand particles in between for achieving the sliding action. And then we have another group led by Ivan Banovic, who from Croatia, who has done a lot of work trying to use different materials for achieving the sliding action. So for example, they use stone pebbles, live stone stand, and different kinds of geosynthetics like geogrid or geomembrane. And then we have the third branch of GSI system, which is based on vibration filtering and scattering. And so there are some similarities with the first branch, but they are actually not exactly creating a soft foundation, soft base underneath the foundation. They put the layer actually at a greater depth or in different configuration. For example, the group from Italy and also from Cambridge actually put it in a V shape. They put the super absorbent polymer in a V shape like this for filtering the seismic vibration. And then we have a researcher from San Marino who introduced a layer at 10 meters depth with a thickness of just half a meter of rubber soil mixtures. And they also find that it can achieve the vibration filtering effect very effectively, and it can also be regarded as a GSI system. And then there is an advanced studies looking at the location of this filtering layer, and that can be done by hybrid simulation, as I tried to show on this diagram. And then we have also researchers who are researching on the use of changes and also backfill it with EPS geofoam to see whether it can filter seismic waves. Actually, the use of trenches is not something new. In the 80s or even earlier, there have been researchers trying to look at the use of trenches for isolating high-frequency waves, but it was not for low-frequency wave like earthquake waves. And so it was just until 2011 when people published the first paper on the use of trenches for isolating seismic waves. Okay, and then in recent years, there have also been some fantastic research about the use of advanced materials like metamaterial for creating the so-called periodic isolation foundation. PIF here means periodic isolation foundation that is based on periodic structures like this one, a layer of reinforced concrete panel with rubber block, for example, and this is 1D PIF. And then they have also researched on the use of 2D periodic isolation foundation and the 3D version of it. And so these are considered some more advanced GSI system, but they are apparently more expensive, I believe. And another fantastic research that can also be regarded as the third branch of GSI system is the use of polyurethane injection. So the concept is that because many of those technologies that I've introduced in the previous slides are mainly for new buildings, right? Some are applicable to existing buildings, but most are for new buildings. And so there is a group of Italian researchers also in collaborating with the Greek researchers who are studying the properties of polyurethane and using it for injecting into the ground of existing buildings through the footing. So as you can see on this site, so they partner with a chemical solutions company, which is called Master Builders. So they are providing the chemicals and then also the injection technique, and they try to inject it underneath the footing so that it can be used to kind of scatter the seismic waves, and it can also provide a seismic isolation effect. So that's all about a very brief introduction of some recent advances of the development of GSI systems all around the world, especially in Europe. And as Juan has just mentioned, because there have been a lot of exciting research happening in this area, so we have launched a special issue on this particular topic of GSI, and I was also appointed as the guest editor of that special issue. And as Juan also mentioned, we also had a special section on GSI in the 17th European Conference on Earthquake Engineering last year. And we will also have another technical section in the hopefully in the World Conference next year. And so to summarize what I've just introduced, so these are the three main branches of GSI system. From the left-hand side, we have the first branch, which is creating a flexible base or flexible foundation for facilitating soil foundation structure interaction. And in the middle, we have the second branch, which is by creating a sliding base. So come back to the first branch. I try to use this diagram because I want to highlight that this first branch of GSI system can also be used for existing structures, because the soft materials or the flexible foundation can just be created at the peripheral of the foundation. Okay, and then on the right-hand side, we have the third branch of the GSI system, which is based on wave filtering or scattering. So this is the diagram showing the polyurethane injection technology that can be used for retrofitting existing structures as well. So to kind of to summarize the advantages of using GSI technologies, of course, without a doubt, first of all, this is for earthquake resilience. And of course, generally, it is all about safety, right? But there is a kind of a buzzword resilience nowadays for describing earthquake-resistant design. And this is not just a buzzword, because for GSI, we are talking about low damage design, because we hope that the seismic energy can be dissipated before arriving the structures. That means the structures would not be damaged even under a strong earthquake. Okay, so it is classified as a low damage, resilient, earthquake resistant design. And the second one is, as you might be able to understand after my introduction, you can see that those technologies are relatively simple. we are just forming the site at the site formation stage, backfilling the material by using quite cheap material like rubber soil mixtures, or even some other materials like EPS geofoam. They are all relatively cheaper, and that's why it can be used more universally in any countries around the world. And for the more advanced technology like the dampers or base isolation techniques using bearings, they require high cost and also high level of knowledge and construction technologies. And that's why those existing advanced earthquake resistant technologies are mainly used for expensive buildings, for important infrastructures, critical facilities, and which are not commonly used for just ordinary buildings, our residential structures, right? And so we believe that GSI system can be universally applied to all kinds of structures because they are cheaper. And the third potential advantage is that, for example, if we are recycling the use of tire rubbers, then we can also have another dimension of advantage that is to achieve environmental sustainability. Not only that we are providing disaster resilience or earthquake resilience, we can also recycle waste materials that can add another dimension of environmental sustainability to this technology. So as a closing remark, I would like to invite everyone to think about it. In the past, drivers thought that using seatbelts alone is adequate. But nowadays, the use of airbags becomes a standard practice. And my question is, can the use of GSI system become a standard practice in the future? And of course, this is also what I believe, and it will happen. Okay, so that's the end of my presentation. Thank you very much for your attention, and I'm happy to take any question.
Okay, thank you, Hinho. Very good presentation. Thank you very much. Yeah, I mean, let's give the floor to the audience in case they have any questions or they want to ask anything related to this topic. Anyone wants to ask any question?
Sorry.
Come here, come here. If not, he's not going to be able to hear you.
Material, how do you bind them together? Sand.
How do you bind them together? You mean the rubber, for example?
Yes, you're putting it under the base of the building.
Okay, so he's asking how you bind the material together with the rest of the soil surrounding the building.
By binding the materials together, bind the particles together, right?
Yeah.
So in fact, we can quite conveniently mix the material together. For example, for soil like sand or gravel, we can easily mix it with rubber, and it can be kind of quite uniformly mixed off-site, and then we can transport it to the site. It would also be applicable if we are using EPS beads. They can also be mixed with soil. But of course, if we are working on a clay material, that will be more challenging. And so we tend to kind of suggest that we better prepare the material offsite. And for example, if we have better understanding about the properties of gravel and the gravel rubber mixtures, then we better get the gravel materials elsewhere and mix it offsite before transporting it to the construction site. And the other approach that we are also researching is about the use of Biden's material. For example, one of my PhD students is looking at the use of bitumen, but that might not be the most ideal material, but we are just experimenting the use of bitumen to bind a different type of soil, gravel or sand with rubber particles. And another possibility is the use of cement. Of course, they can be just lightly cemented. I mean, the rubbers and soil particle can be lightly cemented so that they can bind together easily. Yeah, so there are different kind of binders material that we can use to bind those materials together. Thank you for a very, very good question.
That's a good question, Hinjo, because what we observed also was the fact that if the difference in the size between the different particles between for example, sand and the rubber, they get together, there might be segregation. So some of the smaller particles will go to the bottom, and it might not work in the best functional way or how it's been established. So what you're saying is right. It's like you need to bind it somehow, and there are different ways of doing it. I mean, something that we've tried to do in the lab is to pack it in bags. So with some kind of like plastic around them, but obviously that will affect also the dynamic properties and it will affect the overall performance. So something to look into, indeed. Yeah.
Yeah, and there are also ideas like we put the materials into layers and we put kind of like geomembrane between layers to separate them. Yeah, geomembrane is not something expensive. They can be used for separating different layers, and so it can avoid having this segregation.
Yeah. More questions? Okay, I have a question, Hinjo. I mean, obviously you've been with this research for the last 15 years. Where do you see it going in the next 10, 15 years if you can make a prediction of your own work and the work that other people are doing around you?
Yeah, so the good thing that I would like to share is that there have been a lot of researchers and also practitioners all around the world who are interested in this technology. So, for example, recently we had the damaging earthquake in Turkey, and the researchers there in Turkey who work on GSI system before are kind of are now even more interested in this research, and they are also thinking about implementing this technology in their country. And also there have been a lot of researchers and also practitioners who are actually trying to introduce this technology in the reconstruction after an earthquake or for retrofitting existing structures. For example, in Nepal, there was kind of a series of damaging earthquakes, and they have also tried to introduce the technology to the kind of rural area of Nepal. And they also have prepared a design guideline for potential application. So I believe that there have already been some applications of this technology in Nepal. And also we have colleagues and friends in, for example, in New Zealand, who are closely working on this technology with the industry. And the industry is really very interested in the technology, and they foresee that the technology can be implemented in the very near future within a couple of years. And similar situation can also be seen in Taiwan. I just went there 2 months ago about for the research collaboration, and they told me that the government is actually pushing even harder than they want. The government actually wanted them to write a design guideline within 2 to 3 years. But my collaborator there kind of didn't make the promise because they thought that he thought that it might be a bit too rushed. So that is that particular scenario, they might consider it too rushed. But in other countries, like in New Zealand, they have already done the research for a few years. They see a high potential of really implementing this in practice. And when I talk to a number of researchers in Italy, in particular, they are very keen on finding retrofitting solutions for existing structures, including heritage structures. So imagine if you have a huge cathedral, the historical one, like the one in Vatican, for example. You can imagine that we cannot change anything on the superstructure. On the surface of the structure, we cannot put a dampers there. We cannot even put an isolation bearing, right? But if we can try to find a scheme to isolate it without disturbing the superstructures, that would be ideal. And this is exactly the thing that they are looking into.
Okay.
So I would foresee that in the next 5 to 10 years, there will be more and more trial of applications of this technology.
Yeah, I mean, I will say that obviously the main hurdle in the last few years, it was the lack of investigation, no, and the lack of applicability. But I can see, I mean, based on the number of citations, number of papers being published in the last few years, is that more and more people are aware of how the technology works, and obviously industry is more keen on incorporating it as part of the structures and the buildings. So yeah, I will say moving forward quite rapidly in the next 10, 15 years as well.
Yes, exactly.
Okay, Kinho. Well, thanks a million for. Oh, sorry. Question. Last question. Okay. Yeah. Do you want to come closer and maybe he can hear you better? Maybe they will send you some emails afterwards. Okay, asking lots of questions.
Yeah, that's okay. You're welcome.
Thank you for your presentation. I have 3 questions. I don't know how important they are. Is it single degree of freedom that is used, or multiple degree of freedom that is used during the analysis? That's the #1 question. As the fire resistance has been taking notice of as regards the water, the rubber sand mixture, the total rubber used for the
Okay.
isolated damping.
So you mean like fire hazard that will yeah, imply obviously.
Yes. And my last question is, how much awareness have been given to the Africa? You know, like 5 years ago or 7 years ago, I remember there was a little bit of shaking in, I think in Lagos or Abuja. I can't remember.
Yeah.
Abuja, yeah. So we have maybe a little, not too much, not like
Knowledge
no, we don't even have any awareness about
about this type of technology.
That part of technology and even calculation, even the basic knowledge in college and all that.
Yeah.
So how much awareness has been given to Africa moving forward?
So the first question, sorry, I mean, you were saying about single degree of freedom, multi-degree of freedom system for what? I mean, like interaction
for the analysis, for the modeling
of this type of technology.
technologies.
Yeah, okay, Hinko. So the first one is more to
yeah,
do
yeah.
with soil structure interaction, I would say. And if there's been any,
First of all, thank you very much for all the 3 questions, and they are very, very good questions. And that also shows that you are very interested in applying this technology to Africa. So I'm really glad to hear that. So to respond to your first question about the analysis method, in the diagrams, I try to show a single degree of freedom system, just an inverted pendulum. That is just to simplify the configuration of the structures. And I hope everyone is focusing at the foundation level. Okay, so I didn't mean that the analysis is just based on a single degree of freedom system. So we can do, as Juan just mentioned, do dynamic soil foundation structure interaction, and that is actually based on at least 2 degrees of freedom. And in fact, it is not, because they are also rotational components, and that's why there are actually 3 degrees of freedom. And we can also use finite element modeling to model the exact frame building, and so we have also done that. So that is based on quite many degrees of freedom actually. And so it depends on the purpose of the study. So we can actually do it using a simple structures like 2 degree or 3 degree of freedom system, or we can use a more complicated finite element model. So for the second question about fire hazard, and this is also a very important and practical question. And so far our understanding is that they actually a very little amount of oxygen underground. And that's why the fire hazard is not considered high. But I admit that we haven't done detailed research on this aspect. And yeah, so this is probably something that we all have to look into. But I would say that it is actually the same for any other construction materials. Even for the traditional rubber bearing, there is also a concern about fire hazard, right? So if the rubber is actually melted or burned down, then it would also be a problem with the integrity of the structures. And that is also the same if you are using a steel structures or concrete structures. There is also a fire issue in the design, and we definitely need to consider this as well. And that's why one thing that we are looking into is the use of binder material. So say if it is binded with cement, then it can reduce the fire hazard, or if we can even put, so we are actually experimenting the use of a block of cement, lightly cemented rubber soil mixtures, and it can also be protected by some fire protection material. So it is actually possible, yeah, but it all comes down to the cost of the technology then. Yeah, so more research is needed, and it is an important issue, but it might not be of the highest priority at this stage, I would say, but it is definitely something that we will look into. And for the third issue about bringing this technology to Africa, and this is definitely one of the goal of this research because we believe that this technology can be universally applied, especially as you said, if the people there, if the engineers there, if the public there do not have a high awareness of the earthquake hazard, then they are typically not willing to pay more for high earthquake resistance. And exactly because of this, then we need a low-cost solution. And GSI is one of those. GSI is definitely a low-cost technology. And the second thing is they don't have the knowledge. They don't have the tools. They don't have the construction technologies. And as I've just mentioned, GSI technologies doesn't require advanced design skills. What we need is to replace the original soil from the site, and then we use our conventional site formation technique, then backfill it with different type of GSI materials. Can be EPS geoform, can be SAP, can be RSM. Then the installation part is actually simple. It is much simpler than installing a damper or installing an isolator underneath the building. So that's why GSI technologies were actually proposed with your question in mind in the first place. And it is exactly the reason why we believe that GSI can be universally applicable. So I hope I could address all three of your questions, but I'm happy to take any follow-up questions.
Any other questions? I think they're fine, Kinho. I think that you've given them enough reasons for doing a dissertation on GSI systems in the next few years if they want to. Thanks a million, okay, for well, obviously presenting today. It's getting close to, you said 9 p.m. or 10 p.m. now there in Australia?
9:20 p.m.
Well, as far as
Yeah,
I know,
but
it's your time to do research right now, isn't it?
yes, continue the research on GSI. Yeah.
Very
And
good.
yeah, thank you very much, everyone, for attending this section. And I know that it is kind of probably an extra lesson for you, but many of you are still willing to come to this early morning class. And I think the weather there should still be quite cold in the morning. And so thank you very much for coming. And I hope and I believe that you got some the basic understanding about GSI. And I can see that many of you have developed some interest into this system. And I'm hopeful that you will have this on your mind when you go out to work in the future, or you are probably working as an engineer, then do keep it in mind. And if you want to apply this technology, but do not know how to, please feel free to contact myself, or I think Horn would be another expert that you can contact, and we can work together to make this happen. So thanks again, and I will looking forward to receiving your email for a real project that we can apply GSI together.
Thank you, Kinho. Yeah, I'm sure that they will send you some emails. I mean, like after they ask me about it. Well, thanks a million. Okay, speak to you later.
All right, no problem. Thank you very
Cheers.
much again. Thank you.
Bye.
Bye.